You know those lines on a map that divide countries, right? They seem so clear-cut, but what if I told you there are invisible lines that divide the animal kingdom? Lines that separate tigers from kangaroos. Well, today we're diving into one of the most fascinating of these hidden boundaries, and the brilliant, kinda surprising story behind it.
So think about this for a second. On one side, you've got all the animals we typically think of as Asian, tigers, elephants, orangutans. And on the other, you've got the classic Australian crew, kangaroos, koalas, you name it. If you had to draw a line on the map that separated these two completely different worlds, where would you put it? It seems simple, but the real answer is way more complicated and, honestly, a lot cooler.
For a long time, over a century in fact, the accepted answer was something called Wallace's Line. And for good reason. It's a pretty famous boundary that neatly separates the world of monkeys and big cats from the world of marsupials, animals like kangaroos that carry their young in pouches. This was seen as the great biological divide.
But here's the thing. Nature almost never draws a perfectly straight, hard line. Turns out, between Asia and Australia, there's this huge area with deep oceans and thousands of islands. And in this zone, the two animal kingdoms don't just stop at a border. No, they crash into each other. They mix, they overlap. This incredible biological melting pot has a name, Wallacea.
Okay, so how on earth do you make sense of this jumbled up middle ground? Well, that's where the hero of our story, a guy named Max Weber, comes into the picture. It's 1902. And he looks at this messy region of Wallacea and has a totally radical idea. Instead of looking for another wall, he decides to look for a point of balance.
Now, Weber was actually an expert on freshwater fish, and he proposed this concept of a line of faunal balance. Fauna is just a fancy word for the animal life in an area. So he wasn't looking for a hard stop. Instead, he was hunting for that one specific imaginary line where the number of species with Asian roots was perfectly equal to the number of species with Australian roots, a 50-50 split.
Think of it like a giant seesaw. On one side, you pile on all the animals from Asia. On the other, all the animals from Australia. Weber's line, that's the pivot point, the fulcrum. It's the perfect spot of equilibrium, where everything is balanced, 50-50. If you move west from that line, the seesaw tips toward Asia. If you move east, it tips toward Australia. Simple, right? But also genius.
So Weber comes up with this fantastic idea of a 50-50 balance line. The next logical step would be to, draw it on a map, right? Well, this is where the story takes a really unexpected and kind of weird turn. Let's just quickly walk through the timeline. In 1902, Weber publishes his big idea. Just 2 years later, in 1904, a map showing the line appears. And then, radio silence for 40 years, until 1944, when the map gets a major overhaul. And this sequence of events is the key to the whole mystery.
This brings us to the big, obvious question. What did Max Weber's original map from 1902 actually look like? Where exactly did he draw this famous line of his?
And here it is, the big twist. Are you ready for this? There was no map. In his groundbreaking paper, the very one that introduced this whole concept, Max Weber never drew the line. The man who came up with Weber's line never actually put it on paper himself. Isn't that wild?
So if Weber didn't draw it, who did? The credit goes to a Belgian zoologist named Paul Pelzenier. 2 years later, in 1904, he took all of Weber's data and his ideas about deep-sea trenches being barriers for animals, and he was the first person to actually visualize it, to draw it out. And it was Pelzenier who officially gave it the name we all know today, Weber's Line, to honor the guy who came up with the brilliant idea in the first place.
But that's how science works. It's never really done. Pelzenier's first attempt at a map was just the beginning. As we started to learn more and more about the animals in this region, the line itself actually began to change its shape.
Check this out. On the left is Pelzenier's original 1904 line. See that unique fishhook shape? It kind of snakes its way up and around those islands. But then look at the one on the right. That's the modern version from 1944. It's way straighter, just cutting right through the sea. So what gives? Why the big change?
Well, that change came from an ornithologist, that's a scientist who studies birds, named Ernst Mayr. 40 years after that first map, Mayr redid all the math, but this time he used a huge amount of data on bird species. And because birds can fly, they paint a very different picture of that faunal balance. His work showed the true equilibrium point was actually a bit further east, which had the effect of straightening out the line. And it's really Meyer's version that you'll find in almost any textbook today.
So, after all these different maps and modifications and plot twists, what's the big takeaway here? What does Weber's line really teach us about how the natural world works? Well, the answer is actually pretty simple, but it's also really profound.
The key thing to get is that Weber's line isn't acting alone. It's really the centerpiece of a three-line system. To the west, you have Wallace's line, which is where the Asian animals start to get less and less common. Way over on the east, you have Lydecker's line, which is basically the edge of the Australian animal kingdom. And right there, smack in the middle, at that perfect 50-50 balance point, is our star, Weber's line. Together, all three of them outline this incredible transition zone.
And that, right there, is the true genius of Max Weber's idea. His line isn't a wall. It represents a gradient, a point of equilibrium in this slow, messy, beautiful exchange between two entire biological worlds. It's a powerful reminder that in nature, things are rarely just black and white. It's all about these zones of mixture and complex gradual transition.
And that kind of leaves us with one final thought to chew on. Weber's line shows us that nature often prefers these fuzzy gradients and points of balance over hard absolute divisions. Which really makes you wonder, doesn't it? If nature works that way, why are we as people so often insistent on trying to draw sharp lines everywhere else?